8th workshop on algebraic graph theory and its applications. And actually, during these 4 days, we have talks on different kind of topics. And as for the first day, it is due to problems on Peisert type graphs. So we have 2 talks about these graphs. And then there will be also 2 talks on some bound for polar and affine polar graphs. This talk will be given by Reese Evans, and one more talk will be given by Jack Cullen. It will be a talk about so-called regular graphs, so it is something interesting for us. And we start with the first talk on Peisert type graph, which will be given by Hoi Yip. It is not the first time for him to give a talk. Sorry that we have this gap in time and it is midnight in the United States, well, but it is the only time when it is reasonable to give this talk and to listen your talk for other people from China, Russia, and Japan. So you're welcome.
Okay, so thank you very much for inviting me to speak. I will talk about Algebraic type theorem in Peisert type graphs, and this is a joint work with Shamil Asghari, and Shamil is in the audience. I would like to start with some background on Algebraic theorem. So I will first talk about the classical Algebraic theorem. So this is about questions in extreme set theory, where we are interested in the largest possible size of a K-uniform intersecting family. So here is the definition of K-uniform intersecting family. So we have F being a set system, and for each set in F, it has size K, and it's a subset of the first integers. And for any 2 sets in the family, they are intersecting, so their intersection is non-empty. And we are interested in the largest possible size of F. Given this question, we can try to come up with some simple constructions. And I think the natural way to come up with the construction is that we first fix the element, say 1, and we pick all subset with size K which contain this element 1. Then definitely we have an intersecting family. And we usually call this either a canonical intersecting family or a trivial intersecting family or a star sometimes. And the famous result by Algebraic says that if n is sufficiently large compared to k, then all maximum intersecting families are canonical. So there is no other maximum intersecting family, and all maximum intersecting family must come from this simple construction. And this is also the philosophy in all Algebraic type results. Algebraic theorem is the fundamental result. It's one fundamental result in extreme complex, and there are many generalizations, many analogs. For example, in matchings, orthogonal arrays, permutations, vector spaces, we can all talk about Algebraic type result. Usually, Algebraic type result says that if we want to consider the extreme configurations, then usually they must have some simple construction. They usually have some simple structure, and those kind of structure are also very rigid. And it turned out that this is a common phenomenon in extreme complex. There is also a graph theory formulation for Algebraic theorem. I guess the introduction of graph theory in this context makes it available for us to use tools from, for example, algebraic graph theory to study that. So that's like a nice formulation. So the idea is that we can define this so-called Kneser graph, where the vertices are k-element subset of the first integers, and we draw edge between two vertices if their intersection is non-empty. And then basically intersecting family become independent set in this graph. So the Algebraic Graph theorem says that the independence number of this Kneser graph is given by this binomial coefficient. And also all maximum independent set must be given by those stars or those canonical intersecting families. So in our case, we are more used to talking about cliques. So basically cliques and the independent set are equivalent. So if we want to work on cliques, we just need to work on the complement of the Kneser graph. Okay, so usually for Algebraic Graph type problem, we can associate the comparator problem with a graph, and then we can talk about the EKR property of the graph. So first, we need to describe which kind of cliques are canonical cliques. So usually these cliques are like cliques with large size and it has a simple and rigid structure. And once we have the notion of canonical cliques, we can talk about whether the Algebraic Graph theorem holds. And sometimes I will also use the terminology that acts as the strict EKR property, provided that all maximum cliques in X are given by those canonical cliques. So there is no maximum clique which are not given by those kind of simple constructions. It turned out that algebraic approaches are very powerful in proving EKR type results. Recently, Gorges and Ma wrote a book on Algebraic Graph theorem algebraic approaches, and that book is a wonderful reference for this kind of result. In today's talk, I will focus on the analog of the EKR theorem for a family of cyclotomic strong irregular graph inspired by the EKR theorem for Paley graph. So before talking about our main result, I would like to give some additional background on EKR theorem for Paley graphs. And I'm sure all of the audience here know definition of Paley graphs, but let me just quickly recall that. So the vertex set of the Paley graph is the element of a given finite field. And the two vertices are adjacent if only if the difference is a square in the field. And this is an example of a Paley graph of order 13. And you can try to check those. For example, 1 is adjacent to 5 because their difference is 4, which is a square. And 1 is not adjacent to 3 because 2 is not a square modulo 13. Okay. In the story of EKR theorem for Paley graph, really starting from a paper in coding theory by Van Lin and Mike Williams. And their paper studied certain optimal codes in the sense that they want to have some codes with minimum weight, and their code is related to quadratic residues. So in that paper, they conjecture that if we have a set A of FQ square, so FQ square is the finite field with Q square elements, such that it contains 0 and 1, and it has size Q, and also A minus B is a square for each A and B in the set A. Then the conjecture is that A must be given by the subfield FQ. So it's really easy to check that the subfield FQ forms satisfy these 3 assumptions. But the conjecture is really interesting because it says that the only such subset are given by the subfield FQ. Since I just defined Paley graphs, you can easily see that this conjecture is equivalent to saying that the only maximum clique in the Paley graph of order Q square containing 0, 1 is given by the subfield FQ. Because basically here A minus B is a square for each A and B in A, means that for every two elements in the set A and B are adjacent. So A is just a clique in the Paley graph. Paley graph is just a special Paley graph. Again, I just recall this definition. So given a abelian group G and the connection set S, the Paley graph Paley GS is just the graph whose vertices are element of G, and two vertices are adjacent if only if there are differences in S. In the case of Paley graph, the group G is given by the additive group of the finite field with Q square element, and the connection set is given by the set of squares in the field. Okay, the conjecture by William and McWilliams was first confirmed by Borkhaus around 30 years ago. And then later, Bohr and Fisher provided a similar proof. And in our paper, we also provided like a very different proof. And I will talk about a more general result in the later slides. But before doing that, let me first point out the equivalence between William-McWilliams conjecture and the analog of the EKR theorem for Paley graphs. So before talking about the EKR theorem for Paley graph, we have to define what's canonical cliques. First, we know that in the Paley graph of order Q square, the clique number is given by Q. So there are many ways to see this. You can just use, for example, pigeonhole principle to show that. You can also use tool from algebraic graph theory to do that. For example, it's known that Paley graphs are strongly regular, so you can, for example, use the ratio bound to give an upper bound. And then the lower bound construction is because the subfield FQ forms a clique. So the clique number must be given by Q. So that means the subfield FQ is a maximum clique. Because we are working in a Paley graph, so there are a lot of nice symmetry there. So we can talk about the translation of the subfield. We can also talk about the dilation of the subfield. And it turned out that if we just consider those kind of affine transformation on FQ, you can see that those square translate of FQ are also cliques. So by a square translate, I mean something like A times FQ plus B, where A is a non-zero square and B can be anything. So this is also a clique. If you stare at the Paley graph long enough, you will try to convince yourself that there are no other maximum cliques. At least there are no other obvious maximum cliques. So this all leads to the definition of canonical cliques, where we just define the square translate of FQ as canonical cliques because there are no other obvious construction of maximum cliques. And then in the William-McWilliams conjecture, we are just interested in the maximum clique containing 0 and 1. So if we just normalize this, we can always get FQ if we want 0 and 1 in the clique. So that means Williams-McWilliams conjecture is equivalent to the EKR theorem of Paley graph if we define canonical cliques in this way. Okay, so this is essentially the EKR theorem for Paley graphs. And nowadays, I guess people refer less to the conjecture by William-McWilliams. And anyway, so that's like the history of the EKR theorem for Paley graph. I would like to give a quick sketch of the proof by Borkhaus, because somehow this is somehow this inspire our generalization. So his proof is a very nice application of polynomial method. And the idea is that given a clique C, we want to associate with some kind of polynomial. And in our case, we want to show that if C is a clique with size Q such that 0 and 1 is in C, then C must be given by the subfield FQ. Broca's idea is that we can try to associate C with this polynomial fx, which is the product of x minus C, where C runs over C. And if we set C to be FQ, then this just turned out to be x to the power Q minus x. This is a if and only if condition. So if we can show that fx must be given by fq minus x, then this also implies that C is equal to FQ. And then basically this is a degree Q polynomial, and we want to show that this is equal to x to the Q minus x. So we must show that all the intermediate coefficients are 0. And those kind of intermediate coefficients eventually date back to those elementary symmetric functions in those elements in C. So if we can show that all elementary symmetric functions in C are 0, then we are done. And to show this, we have to use the property of squares and non-squares. We have to use the multiplicative properties of squares and non-squares. Okay, so this is a rough sketch of Broca's proof. Sikla showed that if we replace this kind of squares by, for example, cubic force powers and in general these powers, the proof still work. And this leads to the EKR 0 for generalized Paley graphs. So in the Paley graph, the connection set is the set of squares. But why we just focus on squares? We can focus on cubic. We can focus on these powers. So that's the motivation of studying generalized Paley graph. So it's again a Paley graph defined on the additive group of a finite field of Q square elements with the connection set being the set of these powers. And Sikla just modified Broca's proof to show that if D divides Q plus 1, then we still have the EKR theorem. So here it's important to assume that D divides Q plus 1 because you can show that D divides Q plus 1 if and only if the subfield FQ forms a clique. Okay, and also from the viewpoint of algebraic graph theory, if we do not assume that D divides Q plus 1, then this graph is not a nice graph. So for example, we don't know whether it's a strongly regular graph when D does not divide Q plus 1. So anyway, there are many motivations to impose this condition on the divisibility of D on Q plus 1. Around 15 years ago, Moulin was studying the proof by Broca and Sikla, and she pointed out that somehow Broca's proof rely on the property that the connection set is closed under multiplication. That is the connection set is a multiplicative subgroup. Because in the proof, we need to show that this kind of elementary symmetric function vanish, and that requires us to have some nice multiplicative properties on the on C, and that means we have to have some nice multiplicative properties in the connection set. So if we consider those connection sets which are multiplicative subgroups, then those Paley graphs exactly correspond to generalized Paley graphs. So somehow Moulin's conclusion is that Broca's proof can be only extended to generalized Paley graphs. So in other words, if we want to work on some other graphs, then Broca's proof probably won't work. And the graph she was interested in is the so-called Peisert graphs, and she would like to establish the same EKR type result for Peisert graphs. And I think the reason to consider Peisert graph is not too unexpected, because in a famous paper by Peisert in around 20 years ago, he managed to classify all self-complementary symmetric graphs, and he showed that there is up to an exceptional graph, all self-complementary symmetric graphs are given by Paley graphs and Peisert graphs. So somehow we can understand self-complementary symmetric graph as those graphs with the highest symmetry. So in other words, Paley graphs and Peisert graphs should be regarded as the nicest graphs in terms of algebraic graph theory. So if we know the EKR theorem for Paley graph holds, then it's natural to expect that the EKR theorem for Peisert graph also holds. And apart from the reason I just mentioned, Paley graph and Peisert graph are themselves very similar. For example, they are both conference graph. They are both conference graphs, meaning that they have the same spectrum, assuming that the order of the graph are the same. So all this motivation suggests that the EKR theorem for Peisert graph would hold, but the difficulty is that Broca's proof somehow failed to extend. So I haven't defined Peisert graphs, and I should really do that. So the definition of Peisert graph is also very similar to the definition of Paley graph. So it's again a Paley graph, but now the connection set is given by those powers of G. So the connection set is given by G to the power J, where J is congruent to 0 or 1 modulo 4. And here G is a primitive root of the field FQ. And if we just go back to the definition of Paley graph, the connection set is given by a set of squares. So that means the connection set is actually given by those G to the power J, where J is congruent to 0 or 2 modulo 4. So in this sense, Paley graph and Peisert graph are also very, very similar. So basically, Moulin conjecture that we also have the EKR theorem for Peisert graph, in the sense that we can define the notion of canonical cliques in a similar way, and we conjecture that the only maximum cliques are given by those canonical cliques. This is the definition of Peisert graph, but we can also, of course, talk about generalized Peisert graph by replacing this 4 by an even larger even number. So this is the definition of this power Peisert graph, first introduced by Moulin. So the connection set just does G to the power J, where J is congruent to 0, 1 up to D over 2 minus 1. And when D is equal to 4, we just get Peisert graph. And when D is equal to 2, we get back to the Paley graph. So again, this shows that Peisert graph are very similar to Paley graph. And Moulin conjecture that the EKR theorem for Peisert graph hold. And of course, we can also ask whether the EKR theorem holds for generalized Peisert graph. And again, we need to impose a natural assumption that D divides Q plus 1. And this also appears in the result by Sikla for generalized Paley graph. So this is a natural assumption. Okay, so okay, so basically here we have 4 families of graphs, and for the first 2 families of graphs, we know that they have the EKR theorem, and for the third and the fourth family, we would like to show that they have the EKR theorem. And our idea is that somehow, if there is a way to unify these 4 families of graph as one larger family of graph, then probably there is a unified approach to prove the EKR theorem for all these 4 families of graphs. So that's idea eventually lead to the definition of Peisert type graphs. So this is first introduced by Shamil and I. So our idea is to define a nice Cayley graph where the connection set can be decomposed into the union of FQs that coset. Or equivalently, the connection set is the union of cyclotomic classes. And we can say a Cayley graph is a Peisert type graph of type MQ if S is the union of M many FQs that coset. And the reason we call this a Peisert type graph is that this kind of decomposition essentially come from this kind of decomposition, because here we have like 2 residual classes, but here we further decompose all we further decompose the connection set into like the minimal block, and the minimal block is like a FQ stack coset. And I should point out that this kind of Peisert type graph has already appeared in the literature. And in fact, around 25 years ago, Brower, Wilson, and Shang came up with a systematic approach to construct strongly regular Cayley graphs. And basically, the connection set is the union of cyclotomic classes. So our Peisert type graph is just a special case of their graph, their construction. So that means Peisert type graphs are nice because they are strongly regular. So again, we can try to compute the clique number. And once we have the clique number, we can try to define the canonical cliques. And again, this kind of decomposition makes it much easier to define canonical cliques because from the decomposition, we can just read that which kind of cliques should be canonical. So for example, here C1FQ, C2FQ, up to CMFQ are obviously cliques because this is just a coset of FQ. So it's like essentially closed on the subtraction. So the definition of Cayley graph allows us to say that this kind of subset are cliques. And of course, we are working Cayley graphs, so the chance state of these cliques are canonical cliques. And again, if you stare at the connection set long enough, you can try to convince yourself that there are no other obvious maximum cliques. So in view of EKR type result, it's natural to say that this kind of cliques are the only canonical cliques. And of course, we want to show that all maximum cliques in X are canonical. So if we can show that, then we say that the EKR theorem holds for X. Okay, so once we have this notion of the EKR theorem for Peisert type graphs, then we can really try to ask questions and then try to solve them. So we can try to ask the following questions. So first, we know that Paley graphs and generalized Paley graphs have this GDK property. So immediately we can try to ask whether there is something special for Paley graph and generalized Paley graphs. And I guess Mullin partially answered this question because she pointed out that these graphs are all the only graphs where the connection set is closed under multiplication, so that workhouse proof work perfectly. And then we can try to ask if Mullin's conjecture is true, and we can even talk about the generalization of Mullin's conjecture. So equally, we want to understand whether Peisert graph and generalized Peisert graph have the 3D EKR property. Suppose that the answer to the second question is positive. Then we can again ask a similar question, which is related to question 1. So we can ask whether Peisert graph and generalized Peisert graph are special. And somehow in our main result, we partially answer this question. So they are somehow special, but not really special. So I will talk about that later. Of course, we can talk about other Peisert type graphs. In particular, we are most interested in the case of pseudo-Paley graphs. So that means we consider those Peisert type graphs with edge density half. So equivalently, we are considering those Peisert type graphs whose connection set has exactly Q plus 1 over 2 coset. So this kind of graphs are automatically pseudo-Paley because it's a non-strongly regular graph. Okay, so I guess now I'm finally able to describe our first main result. So our first main result says that the EKR theorem of Paley graph do extend to certain Peisert type graphs, and in particular, the EKR theorem extends to Peisert graph and generalized Peisert graph. So we confirm Mullin's conjecture essentially. And more precisely, we actually show a more general statement. So we show that the EKR theorem holds if we have a Peisert type graph X of type MQ, where M is at most Q plus 1 with 2, and Q is sufficiently large. So we don't want the edge density of the graph to be too large, otherwise we cannot say anything. And the real assumption is the following. So we have to find a multiplicative character such that the character sum over each subset of the connection set of X admit a small cancellation. Perhaps this is not easy to understand. So let me just mention 2 examples of this statement. So for Paley graphs, we just take this multiplicative character chi to be the quadratic character. Then, because the connection set of Paley graph is given by the set of squares, so chi is identically equal to 1 on the connection set. So here, if we want to satisfy this condition, we are just summing dot of 1. So of course, there's no cancellation at all. So this condition is satisfied. So we can just use this result to give a different proof of the EKR theorem for Paley graph. So our proof is very, very different from Workhouse original proof. We can also consider another example which is more interesting. So you consider Peisert graphs. So the connection set here is given by those G to the power J, where J is congruent to 0 and 1 modulo 4. So here, naturally, we can take a character chi with order 4. And for example, we can assume that chi G is equal to I. Then, if we consider the image of the connection set under chi, then we just get either 1 or I. And then if we are summing a branch of 1 and a bunch of I, you can see that there is no, there's again not not much cancellation. So this condition is again satisfied. Okay, so this is our first main result, and in particular, it confirms Mooning's conjecture. And after we having this result, something I want to understand is how limited is this result. So, in other words, given a generic Peisert type graph, can we still apply this criterion to say something? The answer is unfortunately no. So when X is a Paley graph or a Peisert graph, or their generalizations, the choice of the character chi is like almost obvious. So for example, here the connection set has something to do with modulo 4. So just take the character with modulo with order 4. And we are working generalized Paley graph or generalized Peisert graph. Again, there is a natural choice of like character because there is some like modulo D in the definition of connection set. But in general, given an abstractly defined Peisert type graph, it's not clear whether this criterion would be helpful. So by abstractly defined Peisert type graph, I mean, we are just given by the connection set, and perhaps we have the decomposition of the connection set as the union of FQ set. But it's not clear that we can find such kind, because this assumption is really restrictive, because we want the character sum over each subset of the connection set of X amid a small cancellation. So if we take a character chi such that the image of chi on the connection set contains, for example, both 1 and -1, then this condition is of course false. So that means we have to take the character chi very carefully. In general, given a generic Peisert type graph, there is no way that you can do that. And also another difficulty is that given a Peisert type graph, there is no simple way to see that whether the graph has the EKR property. So by just looking at the connection set, it's hard to predict whether the EKR property holds or not hold. And indeed, one can provide a systematic construction of an infinite family of Peisert type graph for which the EKR property fails. And Sergey's talk at like 6 p.m. would discuss more about this, so I won't go into details for this. So I guess all these observations motivate the following questions. So of course, we want to provide a complete classification of Peisert type graph without the with the EKR property. But it turns out that this might be very difficult because this is a special case of a widely open question regarding the EKR property of work graphs of orthogonal arrays. So this is a result in the joint work with Ascali, Inoff, and Lin. So that means probably there's no hope to fully classify all Peisert type graph with the EKR property. So my idea is that maybe we can try to answer a weaker question, namely, maybe you can try to give an estimate on the number of Peisert type graph with the EKR property. Eventually, this leads to a probabilistic version of the EKR type question. So the question we want to understand is this one. So we fix the edge density of the graph, and then we just take a random Peisert type graph with this edge density, and then we can try to ask what's the probability of X such that it has the strict EKR property. So in other words, we want to estimate the number of Peisert type graph X with the given edge density and also with the strict EKR property. I should mention that we are not the first one to study the probabilistic version of the EKR type result. In fact, there are a lot of works related to the probabilistic version of the classical Erdo theorem. So basically, there we are taking a random subgraphs of the condenser graphs, and then we still try to understand what are those maximum independent set, and whether those maximum independent sets still come from those canonical construction. And this is first studied by Bullock, Buckman, Mumbai around 15 years ago. And our second main result is that we can indeed say something about the proportion of Peisert type graph with the strict EKR property. And more precisely, we show that as Q tend to infinity, almost all Peisert type graph of type Q Poisson with 2Q have the strict EKR property. Basically, Peisert type graph of this kind of parameter correspond to those Sino-Russian graphs. So they correspond to those graphs with edge density exactly half. So somehow this family is interesting because it contains Paley graph, Peisert graph, and generalized Peisert graphs. So these results somehow answer the questions I asked in the previous slide negatively in certain sense, because this result says that almost all Peisert type graph of this kind of special parameter have the strict EKR property. So somehow this means that Paley graphs and Peisert graphs are not special because almost surely they would have the strict EKR property. But still, they are nice graph because we can only apply our first main result in this graph. So although this result says that almost all Peisert type graphs are have the strict EKR property, it does not predict which kind of Peisert type graph have the strict EKR property. So somehow they still have certain limitation. Okay, I guess in the remaining time, I would like to briefly sketch the main idea of the proof. So I would like to start from an idea which somehow makes the problem much simpler. And the idea is to treat the graph projectively. And this again relies on the decomposition of the connection set as a union of FQ star coset. So without that, we cannot do anything related to this. So somehow the idea is that because the connection set is a union of FQ star coset, so really we are only interested in which kind of coset appear in the connection set. We are not interested in which element actually appear in the connection set. So that naturally lead us to think the connection set is a subset of the projective line. And then once we realize that, we have to also view FQ square as a subset of the projective line because we are working FQ square. So I guess I have to first define a few maps to get this kind of realization. So first, the classical idea is to view FQ square as a affine plane over FQ, and that easy. We just need to view FQ square as a two-dimensional space over FQ. So we can find the basis, say 1 and V, and then we can define this embedding. by sending A plus BB to A comma B. And then, so this allows us to go from FQ squared to AG2Q. And next, we would like to go from AG2Q to PG1Q. So PG1Q is just the projected line over FQ. And this is easy. We just replace this coordinate A or A comma B by its homogeneous coordinate. Yeah, and then we also need to identify a subset of AG2Q as a subset of PG1Q. And one way to do that is that we just look at the slopes defined by those points. And then informally, we can define the set of directions determined by U. So this is just the difference of those points written in the projective coordinate. And this is a subset of PG1Q. So with this preparation, you can try to make sense of this kind of nonsense. So, so given a Peisert type graph with connection set S, you can try to define the connection set determined by X. So this is given by the composition of the map sigma and pi on S. So first we use the map pi to embed S into the affine plane. And then we use the map sigma to map it to a subset of the projective line. So that this is a subset of PG1Q. So so I call this to be the direction set determined by X. So this is really the like the realization of the connection set as a subset of the projective line. And the reason I do this kind of like nonsense is the following proposition. So it says that if we have a subset of vertices, then C is a clique if and only if the direction set determined by the embedding of C is containing the direction set determined by X. So somehow this means that C is a clique if and only if the direction set determined by C is a subset of the direction set determined by X. So somehow this makes sense. And also if C is a canonical clique, then the direction set determined by the embedding is just one. Okay. So with this proposition, we can try to give a much simpler proof of a result we had earlier. So this result is the key ingredient in our proof. And essentially it says that all maximum clique have a subspace structure. And again, here we need to assume that the edge density is at most half. Otherwise, we cannot say anything. So with the previous projective observation, this result is really easy to prove. So the idea is that if you just pick a generic subset of the affine plane, then you would expect that there are a lot of directions. But somehow, if the number of directions is small, then you would expect that there is some algebraic structure for the point set. And actually, a famous result of Bohr using, again, powerful polynomial method, so that this kind of special algebraic structure is exactly the is exactly the subspace structure. So so here, because M is at most Q plus 1 over 2, so the direction set determined by X is at most Q plus 1 over 2. And somehow we can understand that as the direction set determined by X is small. And then if we go back to this proposition and look at the first item, we can see that the direction set determined by every clique is small. And then we just apply this result by Bohr, and it's immediately implied that all cliques must have a subspace structure because the direction set determined by the clique is small. So this is a key ingredient in our proof of both results. Once we have this subspace structure, we can use a lot of tools, say for number theory or algebraic graph theory, and also algebraic geometry. So first, to upgrade the subspace structure to a subfield structure, we can try to use character sum estimate to detect whether a subspace is given by a subfield. And this is guaranteed by the following result. So essentially, it says that if we have a subspace with the right size, but it's not given by a subfield, then for any non-trivial multiplicative character chi, the character sum over the subspace V must have some non-trivial cancellation, provided that Q is large. So here we need this factor 2n over square root Q to be less than 1, otherwise this estimate is trivial. So this is a consequence of the character sum estimate by Katz and Ritz. And then if we want to show that our subspace must be a subfield, our idea is just to provide a lower bound on the left-hand side. And if we can show the lower bound is greater than the upper bound, then we are done. So that's why we impose certain kind of non-cancellation condition on the character sum over those subset of the connection set. And formally speaking, we have the following result. So this is the formal version of our first main result. Essentially, it says that if we can find some non-trivial multiplicative character chi such that the image of the connection set under chi is somehow lower bounded, in the sense that the average value of any multi-subset of this set has a large absolute value, then we have the EKR theorem. That's essentially because of this estimate. So if this set is like epsilon lower bounded, then we can give a lower bound on the left-hand side, and the lower bound is exactly given by epsilon times V, because the average is at least epsilon, and the number of elements is given by V. So if epsilon is greater than 2n over square root Q, then we get the contradiction if V is not a subfield. So that's how we prove the first main result. Yeah, so now I'm running out of time, so I guess I'll quickly sketch the main idea for the proof of the second result. So the second result says that almost all Peisert type graph of this type have the strict EKR property. And our idea is to estimate the contribution of those non-canonical cliques. So we know that those non-canonical cliques have to be subspaces with the right size. So we can use Gauss-Mainian to estimate the number of non-canonical cliques. And then it remains to show that each non-canonical clique can actually appear as a clique of in a small number of graphs. So I mean, so for each subspace which is not a subfield, we want to show that it can be only the clique of field graphs in this family of graphs. So with these two estimates, we can prove this result. So to prove the second estimate, we need more tool from the EKR type result for Peisert type graph, which I didn't go into deeply. And I just want to quickly mention that actually we can show something stronger. We can actually show that almost all Peisert type graph are stable in the sense that this kind of canonical cliques are stable. And it basically means that if we have a clique with size close to Q, they must be containing a canonical clique. So in other words, there's a gap between the size of the second largest maximal clique and Q. So this is known as like the stability type result in EKR type result. And to prove this result, we really need to from algebraic geometry, and in particular algebraic curves over a finite field. So in particular, this says that almost surely canonical cliques are stable in most Peisert type graph in this family. But unfortunately, this does not say anything about Paley graph. So it does not say anything about the stability of canonical cliques in Paley graphs. And this question has been studied by Baker around like 30 years ago, but as far as I know, there's little progress towards this problem. And I think the best known result is that if we have a Paley graph with order Q squared, then if we have a clique with size Q minus 1, it must be containing a canonical clique. But that result is kind of like trivial or like not important. So if we want to understand the size, if we want to understand those cliques with size Q minus 2, we have to use some non-trivial tools. And I hope we can use some tool from algebraic geometry or maybe algebraic graph theory to make progress. So that concludes my talk, and thank you very much for your attention.
Thank you very much for your very interesting talk. Are there any questions to Hoi, please? Yeah, it was great. It was really great. Yeah, I like this topic because, well, very much like, because you have a lot of different methods and approaches from different areas, field theory, character theory, number theory, combinatorics. Yeah, so interesting. Well, okay, any questions, please? Okay, I have just one question about this question on the last slide. So what is your feeling? What do you expect actually? What is the answer? What would be the answer on this question?
So Baker and others actually conjecture that if we have a clique of size greater than Q over 2 in the Paley graph of order Q squared, they must be contained in a canonical clique. But the best known result is Q minus 1. So you can see that there's a huge gap between Q over 2 and Q minus 1. So Q minus 1 is almost obvious, it's almost trivial. And if we want to do Q minus 2, I guess our current technique cannot achieve that already. So it's widely open.
I see. Thank you.
Yeah, thanks for a nice question.
Okay. Any other questions or comments? So Shamil is with us. Would you like to say something about this topic?
Yeah, I think it's striking that for this question, we don't know how to show that if a clique has size 0.9999 times Q, then it must be contained in the canonical clique of size Q, exactly. So I think that's the question. It'd be nice to make progress.
Okay, thank you, Shamil. Any other questions? Well, okay, if not, then let us again to thank Hoi. Thank you. It was very nice. Yeah, I enjoy a lot. Thank you very much.